By now, we've been dealing with chemical equations, reaction equations, for quite a bit. And yesterday, in the example 8.1, they used this reaction where ammonia, NH3, reacts with sulfuric acid to produce ammonium sulfate, NH4(2). Okay, so this is the base reaction that we're looking at in example 8.1. Now, don't worry so much about stoichiometry right now. Let's look at this and look at it from a module 7 kind of a perspective. Okay? Whenever we're going to answer a stoichiometric question, and a stoichiometric question is a question that says, given a certain amount of one component in this reaction equation, tell me something about another component in that reaction equation. Yesterday, I mentioned to you, and I want to reinforce this idea that when you're doing stoichiometry, this base equation is the beginning of your understanding of reality, what's true. You know, the big fancy word of epistemology, what do you know? And how do you know what you know? And how do you know if you know? It's actually a study of knowingness, whether you know or not. This idea here is when you start with an equation, all these relationships you're going to come up with start from this equation. And this equation here right now is not balanced. All this equation is telling us right now would be the way we would first write it down if you were listening to someone say, hey, Jessa, for example, I got some ammonia and I want to mix it with some sulfuric acid. It's going to make ammonium sulfate. And you're going, okay, I'm not now making a statement about relationships. I just want to get down what the elements of it are. So in this case, we're saying ammonia reacts with sulfuric acid to produce ammonium sulfate. Okay, now I have the components that are involved in the reaction. So we're always going to write this down, and I'll refer to this as the base equation. This is the base equation. It's not balanced. This is the base. Everything now is going to build on this. So the next step, so we have a base. And from the base, we move up to the balanced. Now, when I say base, later on you're going to get a little more savvy in chemistry. And you're going to say, wait a minute, base or acidic? Basic or acidic? That's not what we're talking about right now. Just as this is an acid because it's a hydrogen donator. This has hydrogen in front. We're going to learn later. This is an acid, and it's going to donate protons, and something else is going to receive those protons. So it's the base. This is something different. I'm talking about the equations. Maybe I'll add the EQ here. So the base equation is just what plus what makes what and what and what. Then the balanced equation. I need to go through and do a module 7 kind of balancing the atoms. Remember, when we're doing an equation, we're really talking about the atoms that are available to us in the reactants that produce the atoms that make up the products. They're not necessarily located they're not necessarily located in any particular molecule. We're going to break these down and build it back up into something new. We're going to take all these Legos, pull them apart, and make something new. But the deal is, when we start with a certain amount, that amount which actually reacts, and that's part of the next lecture, which hopefully we'll get into before we leave today, those that actually react, the number of atoms we start with have to equal the number of atoms we end with of each type of element. So, let's assume that this is going to be a full reaction. Everything's going to be used up. In order for everything to be used up, we're kind of talking about the ideal recipe. What does the balanced equation look like? So this is the base equation. Let's balance it. We said before, if you remember from yesterday, looking from left to right, we've got nitrogens here. We've got 1 in the reactant side. We have 2 in the product side because there are 2 NH4 molecules in ammonium sulfate. So to have 2 nitrogens, we need to have at least 2 here. And so we've got 2 nitrogens. 6 plus 2 is 8 hydrogens. 8 hydrogens. 1 sulfur, 4 oxygen, 4 oxygen. So this is our balanced equation now. We've taken our statement of action in the reaction, from this reactant and this reactant form this product, and now we have more information about it. What we can say now is not only do I have ammonia and sulfuric acid combining to make ammonium sulfate, but I now have these stoichiometric coefficients in place. Stoichiometric coefficients in place. And what do these coefficients tell me? I've got a 2, I've got an implied 1, and I have another implied 1. What do they tell me? Yes, sir. The relationships between the number of molecules or atoms or the relationship between the moles, right? Because they're actually just ratios. Let's say we're talking at the molecular level. Remember that these coefficients tell us that there are 2 ammonia molecules that react with 1 sulfuric acid molecule to produce 1 ammonium sulfate molecule, right? We should be good with that by now. 2 of these and 1 of these make 1 of these. In terms of pieces, we have 2 pieces and 1 piece that make 1 piece. This is a buildup, right? We've taken these 2 and this 1, we combine everything we've got, and it makes this 1 new structure. And just as 2 molecules and 1 molecule makes 1 molecule because of the stoichiometric coefficients, we can also say that 2 dozen and 1 dozen make 1 dozen, that 2 score and 1 score make 1 score, and ultimately, 2 moles and 1 mole make 1 mole. Right? So that's our base equation, now balanced. And this balanced equation, and it has to be a balanced equation, now becomes the way we figure out how everything relates to everything else. If I know that I have a certain amount of any one of these molecules that are represented in this equation, if I know that I have a certain amount of any one of them, I know how much of the other ones I either need or will be produced if that amount is completely reacted. That amount is in pieces, so it's going to be our piece count. It's not in grams. Got to keep this straight, because this is one of the most common errors, is people say, let's say the question tells you how many grams of something you have. And you say, well, I use twice as much ammonia as I do sulfuric acid, so since I have 10 grams of this, I must need 5 grams of that. No. It's not in the mass. It's in how many pieces you have. It is correct to say 2 molecules and 1 molecule. It is correct to say 2 moles of molecules and 1 mole of molecules. It's not correct to say 2 grams and 1 gram. Okay? We're not talking mass. We're talking count. Most commonly with regard to moles. So this is our balanced equation when we're dealing with example 8.1. We've got ammonia and sulfuric acid react to produce ammonium sulfate. The question that they originally asked us was, given this, if she ends up making 12.2 moles of ammonium sulfate, how many moles of ammonia were used? Now, the way we've learned it and the way the text has shown it up to this point, what we're looking for now is, given this is our reality, this is our world, looking at this balanced equation, we need to find something that relates what we know in terms of count. In this case, we know we're looking for producing 12.2 moles. How does this 12.2 moles of this molecule relate to the count necessary of this molecule? So the first thing I need to do is look back to my true statement. This is my basis of reality, the balanced equation, and say I need something that relates. When we say relates, I want you to write down a statement of equality. I say the word relates to, but for you visually, thinking of it as math, use the equal sign. Something that relates an amount of what we know to a certain amount of what we are looking for. How do the moles of ammonia relate to the number of moles of ammonium sulfate? Just look at the stoichiometric coefficients, right? 2 moles relates to 1 mole. This equation tells me that 2 moles is related in some way to 1 mole. And in the same way, 1 mole of sulfuric acid is related to 1 mole of ammonium sulfate. Okay? Sometimes I use this, it's related to or proportional to, but the standard way of recognizing is writing the statement of equality. Why? Because we're going to come up with a multiplier, a unit multiplier kind of a deal. If I know I'm looking for moles of ammonia, I'm given moles of ammonium sulfate, a certain number of moles, that's what I'm given, and I know I need to multiply it by something to get me to a number of moles of ammonia. See? I started with moles. I've been given this. Matter of fact, I've been given that I'm looking to make 12.2 moles of that product. 12.2 moles of my product. I need something here that's going to give me moles of ammonia, so I need some relationship between moles of ammonia on my numerator. My denominator needs to be moles of ammonia sulfate. And I get this multiplier from this statement of equality. 2 moles of ammonia per 1 mole of ammonium sulfate. Moles, moles. Check my units. Moles of ammonium sulfate, moles of ammonium sulfate, moles of ammonia, moles of ammonia. My setup is correct. Now all I need to do is the actual math through the coefficients. 12.2 times 2 divided by 1. So I'm going to take this and double it to get 24.4. Now, let's kind of look back to our equation and see if this makes sense. Does this make sense given this? I see that if I have 1, it required 2. If I had 1, I need twice as much. If I have this, requires twice as much, and it works. So all I'm doing is taking how they relate to each other in proportion here, and then saying, okay, rather than making 1 mole, I want to make 12.2 moles. How much do I need? Another way to think about this is a recipe. This right here is your recipe. You're chemists, you're bakers. Not like in Mr. Baker, but like we're in the kitchen making stuff, right? Cooking and baking is chemistry. You have a recipe that you've pulled out. Here's great grandma's recipe for ammonium sulfate. All right, it's time to make ammonium sulfate. We need 1 mole of ammonium sulfate. Well, the recipe says for 1 mole of ammonium sulfate, I need to go to the cupboard and pull down and get 2 moles of ammonia and 1 mole of sulfuric acid. So you go and you get 1 mole of this and 2 moles of this, and you mix them together and you make 1 mole of this. Great. But guess what? You're having a party. And a bunch of people are coming over. And so rather than making 1 mole, you find out you actually need to make 12.2 moles. So what would you do? Well, let's make it something we're used to. You're having a party, and you're making a dozen cupcakes. You have a recipe to make a dozen cupcakes. But then you find out that the guest list is larger than you thought. Instead of 1 dozen cupcakes, you need to make 5 dozen cupcakes. What do? You take the recipe for 1 dozen, and you multiply it 5 times, right? Now, There's a practical limit to that because you can only get so much material in there before, and professional bakers will tell you this, you can only get so large before the metaphor starts to break down. But let's pretend we can do that. But we could, rather than taking 3 eggs to make a dozen, we need 15 eggs to make 5 dozen. That's exactly what we're doing here. We're saying our recipe calls for 2 of these and 1 of these to make 1 of these. But we're not trying to make 1 of these. We're trying to make 12.2 moles of those. So 2 moles and 1 mole make 1 mole. So 24.4 moles and 12.2 moles make 12.2 moles. That's stoichiometry. This is the setup, and this is the way they teach it in the book. Now, at the end of yesterday's presentation on the video, I showed you the way that I taught it last year, and I told you that this is really another way of using the mole bridge diagram. So I'm going to erase this right now, okay? Yes, sir?
On the answer, when you got 24.4 moles NH3, would it be NH6 instead of 2?
No. No. We're looking at this product here, or this molecule right here. All I'm doing is messing with the coefficient. I don't have the authority to mess with the subscripts. When I balance it, when I balance it even, I don't mess with the subscripts. I can only mess with the coefficients, okay? So if I change that to NH6, it's a different molecule. That's not the same thing I had before. All I'm doing is changing. It's kind of like saying this is eggs and this is butter, okay? I wouldn't change it to something other than eggs when I multiply it by 2. It's still going to be 2 eggs, 3 eggs, 5 eggs. It's the same thing, just more of them. So the coefficient is how many of them you have. All of this, including the subscripts, is what do you have? Right. Now, let me look back at this balanced equation. And the process that I taught last year, or the method that I used last year to solve this kind of a problem, you had to start with the same first 2 steps. You had to write the base equation and then balance it. So you can't get past that. You're going to have to write the base equation and then balance that base equation before you can do anything else. Now, when we looked at the problem last year, what I would do is I was always going to leave a little bit of space underneath my balanced equation. And whenever I was given an amount of one thing, I would write it kind of like skip a space and go down a little bit. In this case, the problem says that we're going to end up with 12.2 moles of ammonium sulfate, right? And the problem asked us how many moles of ammonia. So below this, I would come down, kind of like skip a space mentally, and write moles. Now, what I would do then was recognize that I leave a space here because sometimes in the future, in this module, they're not going to give us the number of moles, they're going to give us the number of grams. And let's say the problem, rather than saying that you produced 12.2 moles, said that you produced 138.7 grams of ammonium sulfate. Okay? Hypothetically. Well, if I were given grams, I can't use stoichiometry to relate grams to grams. Like I said before, 2 grams and 1 gram does not make 1 gram. The conservation of mass, right? It doesn't work that way. It doesn't relate in that way. It only relates in count, not in mass. So I've got to have a way to convert my mass into my number of moles. Over here, real quickly, let's look at the one arm of our molar bridge diagram. We have moles. And if you remember, this one side over here, we had mass. The component that goes between these two is our molar mass. When we have the mass times the molar mass, so the moles times the molar mass gives us our mass, and our mass divided by the molar mass gives us the number of moles. So if I told you I have a certain number of moles of a compound, you could figure out the molar mass of that compound, and you could compute the mass. If I gave you the mass, you could again compute the molar mass, divide by that, and get the number of moles. This is the same thing. On this kind of a diagram, what we're going to show is this movement from here down to here is going to take us from mass to moles. And to go from mass to moles, we're going to divide by the molar mass. So if I knew the molar mass, I could compute the molar mass of ammonium sulfate, right? I go through and add up the individual atomic masses of the number of each element in that molecule, and then say it's so many AMU. So for every mole, it's that many grams. Well, if I were given a number of grams, I would then divide it by the molar mass to get the number of moles. In this case, we're given the number of moles, so we don't even have to do this step. We're spared the misery, or the excitement, however you look at it, of computing the molar mass and doing the math to get to the moles. This problem gives us the moles. From moles, we need to get to moles of whatever it is we're looking for, in this case, ammonia. The question asks us to solve for the number of moles. The question could, and will very shortly, ask us to solve for the grams, in which case we would move up to the mass, and to get from moles to mass, we're going to multiply by the molar mass of this molecule, of one of these molecules. Okay? So as we continue to perfect this method, wherever you're starting from the given, you're going to go from the given mass to the given moles by dividing by the molar mass of that molecule. You're going to move from moles of the given to moles of the unknown using the stoichiometric coefficients, and we'll do that in just a moment. And then you're going to move from moles if necessary. If it says solve in moles, there's your answer. If it says solve in grams, you've got one more step. You need to multiply by the molar mass of that molecule to figure out the grams of that molecule. Again, this is the simplest first shot at this, and it gives us moles and asks us to solve for moles. What I do now, since I'm looking at this molecule and this molecule, I draw a little box. And I look at the formula, and I say, what are my stoichiometric coefficients? My stoichiometric coefficient of what I'm driving toward, ammonia, is a 2. What is the coefficient of what I'm driving from? I'm driving from ammonium sulfate. The stoichiometric coefficient here is an implied 1. Okay? So this is the setup for the math problem. If I'm given mass, I can compute moles. For moles, I'm going to do math to get moles, and for moles, multiply by the molar mass to get mass. They gave me moles, and they asked for moles. So the only part I have to do in this problem is this lateral part right here. Now, as I'm moving from what I've been given or asked, what I've been given for here, what I've been given here, moving to what I've been asked for here, I have to do some multiple here, some multiplier. It's going to multiply by something that comes from these two numbers. And the technique that I described on the video yesterday was, as I get to this place, whatever number I hit first, in this case moving from right to left, I hit the number 1 first. And that hitting it first drives it into the denominator. As the 1 here gets driven into the denominator, that makes my multiple 2. You see that? 2 to 1, the 1 falls under the 2, and so to go from here to here, I multiply by 2. 12.2 times 2 is 24.4 moles. That's my answer to the question. If given 12.2 moles, how many moles of NH3, ammonia, do I need? I take this and I multiply it by 2 to get this. You can see also that if I were given 24.4 moles and I didn't know how much ammonium sulfate would be produced, I could go from this side across this way. And as I go across this way, 24.4 times, as I hit the 2, it drives to the bottom. So going from right to left is multiplied by 2. Going from left to right is multiplied by 1/2. Because the 2 would be driven down below the 1. 24.4 times 1/2 would give me 12.2 moles. Okay, so this technique helps you travel between moles to moles, and it relates them from these numbers here, which are drawn from the stoichiometric coefficients. If you were given mass, you'd have to convert to moles before you did this. And if you're asked for mass at the end, you'd have to convert from moles back up to mass. Okay? So the flow is always going to go from what you've been given to what you're asked for. In this case here as well, we could also say how many moles of sulfuric acid are required. I'm actually going to draw this portion inside this other portion. But let's say that it came down here, went across here, you had your own relationship here, comes to here, and then back up to here. My stoichiometric coefficients are implied 1 and implied 1. So it's pretty straightforward. If we've got 12.2, 1 to 1 means you multiply by 1 and you get 12.2. It should be obvious because their coefficients are the same. For every 1, it makes 1. So 12.2 requires 12.2. And 12.2 requires 24.4. So the recipe is 2 and 1 make 1. And again, know the process because the numbers aren't always going to be this straightforward. They're always going to be whole number ratios in here. These numbers start to get a little crazy, you know, like 0.003579, whatever, you know. So know the process. If you're one of those folks that do okay in math when the numbers are obvious, like if a dozen is 12, how much is 2 dozen? 24. How much is a half a dozen? 6. Okay, but if you can't do the same thing with moles, it's because you're doing it using logic rather than doing process. This is the process that'll get you through this. This is just a graphical way. It's another way of doing the same thing we did before using the unit multiplier. This is the unit multiplier. It just does it in a graphical way that might be easier for you to set up, right? What this is doing right here, just so I'm sure you have it, what this represents is 2 moles of NH3 per 1 mole of NH4,2SO4. It's 2 moles of ammonia per 1 mole of ammonium sulfate. That's here. That is the statement of equality that we wrote out longhand before. It's the same process, just shown to you graphically. Is that helpful? Okay, so in terms of process, I want you to understand what's happening. To me, that's most important. Sometimes getting right answers helps you learn the material. Okay? So as you do it, you're successful in getting the right answer. Even if you don't understand why this works quite yet, keep plugging away at it. Keep doing it. And maybe, again, it'll be like one of those pictures where you're looking at it and don't see the picture and suddenly it draws out at you at 3 dimensions. Okay? Chemistry can be like that sometimes. This is another way to look at it so that maybe it'll pop out for you. Now, the next section in our book talks about this idea of limiting reactants and excess components. If we use this same formula here, we're using the ammonium and the sulfuric acid to make ammonium sulfate. I'm going to erase some of this other stuff. Is it okay to erase this? Those of you taking notes? Okay. Let me get rid of this. This idea of limiting reactant. Think of a limiting reactant, well, not as if, because this is actually what's happening. We talked about complete combustion and incomplete combustion. Remember we said we had a carbon, hydrogen, oxygen chain, a CXHYOZ molecule, some kind of CHO molecule that was experiencing complete combustion. It was combusting with O2 and producing CO2 and H2O. And that reaction took place until we started to experience incomplete combustion. What was happening at incomplete combustion? How does incomplete combustion compare to complete combustion? Producing carbon monoxide rather than carbon dioxide, right? Good, Lexi. Okay, so what was happening there? We were producing something different. Why were we producing something different? Insufficient oxygen. The equation changed because we ran out of something. Now, in the case of incomplete combustion, we can still make a product of carbon monoxide rather than carbon dioxide, and so the reaction engine keeps driving. And I'm going to use that phrase, the reaction engine. When I say the reaction engine, I mean, hey, you've got fuel, you've got energy, the reaction takes place until what happens? You run out of fuel, right? You go out to start your car in the morning because it's a little bit cold, and you turn the engine on, you turn the heater on, you turn the windshield wipers on, you go back in the house, you come out, and the car's dead. What happened? You ran out of gas, okay? The car died because it ran out of fuel. I'm going to be talking about the reaction engine sometimes, and all I mean by that is whatever it is that's making the reaction occur. When you run out of something that's required for the reaction, the reaction engine stops. So let's look back at our base equation again of ammonium, hydrogen, or sulfuric acid, and ammonium sulfate. This is our reaction. Do you agree with me that as long as we have enough ammonia and enough sulfuric acid, that this reaction is going to keep producing this product of ammonium sulfate? I mean, if you've got 2 to 1 and they keep mixing, you're going to keep producing, right? What happens when we run out of something? It stops. The reaction engine stops. And I'll submit to you that the reaction engine here reacts to produce. That's kind of where the reaction engine is. Looks back over here and says, you know what? It's going to stop working as soon as I run out of one of these two. Let's say that I have a pool full of ammonia. A swimming pool, full of it, right? And I walk over and I pour a cup full of sulfuric acid into that ammonia. Am I going to produce ammonium sulfate? Yeah, I will, right? However many molecules of sulfuric acid are in that cup, every one of those molecules is going to combine with 2 molecules of ammonia. It's going to produce 1 mole for every, or 1 molecule for every molecule, right? But when all of the acid that I poured in there, in my cup full, when it's all used up, what am I going to have left in the pool? When this is all used up, some of this was converted with this to make this. So I'm going to have ammonium sulfate in the pool, right? Because some of it was produced. Am I going to have any sulfuric acid left in the pool? No, it's all gone. Where'd it go? It went to build these. But I still have a whole stinking lot of ammonia left in the pool, don't I? Because there wasn't enough sulfuric acid to combine with all the ammonia to make ammonium sulfate. So what has happened in that example is I have one reactant which I have a little bit of, and another reactant which I have a lot of, and all of the reactant which I have very little of is used up. And there's a whole bunch extra of the other reactant which didn't get touched at all. That's the idea of the limiting reactant. In this example, my sulfuric acid is my limiting reactant. It's all going to be used up. And I'm going to have excess of something else that's left behind. Now, why this becomes important is because when we have our balanced reaction, if I say, okay, 2 and 1 make 1, this is the ideal recipe. This is the perfect formula. In a perfect world, from a reaction standpoint, I would always have 2 and 1 to make 1. But let's say in real life, I find that as I mix these things together in a beaker or something to make this reaction take place, I actually, this is ideal, and this is actual. In the lab, let's say actually in the lab, I combine 4 NH3 and 1 H2SO4, and it's going to react to produce a certain amount of NH42SO4, sulfuric acid, or excuse me, ammonium sulfate. It's going to produce a certain amount, but how much? How much? If I know that the correct balanced equation is 2 and 1 make 1, what am I experiencing here? 4 and 1 make how much? Well, I don't even want to write it in this form because you might start to think this is an actual equation. It's not. But what I hope you see is that if I double this, and let's say if I doubled this and I doubled this, what would I expect to get? Double that amount, right. If I double everything, if I double them all, it's still an appropriate balanced reaction. But if in actuality, rather than 4 and 2, I had 4 and 1, I'm actually only going to produce 1 I'm only going to produce one because for every, this is my limiting reactant, right? It's going to run out. And when it runs out, this is all left over. So what I'm actually going to have, if I have one, how many of this is it going to use up? Every one uses up 2. So what I'm going to end up with is actually I'm going to have 2 left over. Okay? I'm going to run out of something, and I'm going to have extra of something. Normally when we do a reaction equation, we like to have reactant plus reactant produces a product and nothing else, no leftover. Here what I'm trying to describe is, hey, if I double my amount of ammonia, but I don't double my amount of sulfuric acid, I can still only make 1 mole of ammonium sulfate. Why? Because this will all run out after this reaction engine happens one time. But I'm going to have leftover. And so ultimately, when you know that you have an actual in the lab kind of a thing going on, you find out your limiting reaction or your limiting reactant, your whole ability to produce product is going to be limited by your limiting reactant. And once you know the limiting reactant, you can figure out how much product can be produced because it's only going to go until that reactant is completely used up. In the book, it gives the definition, and we're going to be doing this lab kind of not in sequence with the book, but we will do this lab. And hopefully what you see is you've got 2 reactants. If you have excess of one, a certain amount of product is produced. If you have a perfectly balanced reaction, you have a larger amount of product is produced. And then when you have an extra amount of the other reactant, it doesn't make any more product. It stops after about the same amount of product is made. But in the book it says the limiting reactant limits the amount of product that can be formed in a chemical reaction. It's the definition. The limiting reactant limits the amount of product that can be formed in a chemical reaction. So whatever you run out of, it stops the reaction. It's not going to change your actual, or excuse me, it's not going to change your ideal. What would be the balanced reaction formula? What we're talking about now is what actually happens in the lab when you mix these things, kind of doing the mad scientist. What happens? One of these is going to run out first. And it's going to produce a certain amount of product based upon this relationship, but you're going to have leftover reactant that's not limited. That isn't your limiting reaction.